Here's our first QQT for Unit 6. Colliding blocks compress different springs. So you've got your figure, and we've seen this figure before. We've got block B at rest, block A scooting along. At time T2, they collide, and they stick together in this case. At T3, block B makes contact with the spring, and at T4, the spring is compressed a maximum distance and the blocks are instantaneously at rest. No friction between the block or the surfaces. Okay, so student observes the experiment and makes the claim, since some mechanical energy is dissipated when the blocks stick together, the momentum of the two-block system decreases. So here we are again, combining conservation of momentum with conservation of energy. And so the first part of his statement is correct because some mechanical energy is lost in that perfectly inelastic collision. The momentum of the two-block system remains the same. Okay, and remember the criteria for that is no external forces, right? So the question reads, indicate whether the claim is correct or incorrect and explain why. So we say, you really don't have to address the part that's correct about mechanical energy being dissipated. Just address the part that's incorrect. The momentum of the system does not decrease because there are no external forces. That's part A. 1 point for saying it's incorrect and attempting to explain why, and 1 point for indicating why the momentum doesn't change. Part B makes another claim, or another student. When the blocks collide, the total momentum of the two-block system doesn't change, so the kinetic energy must also be constant. So they sort of took the opposite view. They're like, wait a second, momentum doesn't change, so kinetic energy doesn't change. Well, we know that that's not true. Unless the collision is perfectly elastic, we are going to lose some kinetic energy. So even though the momentum remains the same, the kinetic energy of the system does decrease. So 1 point for saying it's incorrect with explaining why, and then 1 point for explaining why kinetic energy isn't constant. So that is part B. Part C asks us from the time interval from T3 to T4, is the magnitude of the acceleration of the two-block system increasing, decreasing, or constant? So we've got to look back to see what's happening between T3 and T4. Between T3 and T4, the block is actually compressing the spring. Now, at T3, this question was a little bit tricky because remember, they are slowing down, but they're not asking for that. They're asking for the magnitude of the acceleration. So look at your diagram again. Look at T3. There's no friction anywhere, so the system is not accelerating. The collision has already happened, and block A and block B are moving forward with their final speed. Once it hits the spring and the spring starts to compress, that slows the system down. So the system does slow down, but the magnitude of the acceleration increases. So I hope I didn't overcomplicate that. At T3, the acceleration is 0. Between T3 and T4, the acceleration is not 0, so the magnitude must be greater than 0. Let's see, another way you could have put that is that since the force increases with the increasing x, the acceleration also increases. So 2 points there. 1 point for saying it increases, plus an explanation, and then 1 point for the correct explanation. All right, on to part D. During the time interval from T3 to T4, all right, this is the time that the spring is being compressed. Does the spring do positive, negative, or zero work on the two-block system? Okay, so remember, work results in a change in kinetic energy. And so if the change in kinetic energy is negative, or if it decreases, then work is negative. So the answer is that the spring does negative work. There's a couple of explanations that you could use there. You could say that the spring is exerting a force in this direction while the objects are moving in this direction. And so that you could say that since the angle between the force applied and the displacement is 180, the work is negative. Or you could also say Since the kinetic energy decreased, it must have been negative work. There may be other ways to say that, and if you want to bring that up, let me know. But I think those were the two that came to mind for me. Then we're going to change things up a little bit. In case 2, the setup is identical to case 1, but we're using a stiffer spring. Okay, K2 is greater than K1. Block A slides with the same speed as before. And now we're going to compress a maximum distance T2. How does the maximum spring compression in case 2 compare in case 1? And it's less. It's going to compress less. Right. Oh, part F is we have to explain. I was going to say, why aren't we explaining? So part F, 1 point for saying it's going to compress less. And then part F, wait, what did I just say? Part E is less and 1 point there. So part F says briefly explain your reasoning. So what happens is that the kinetic energy that the blocks have is going to do, the blocks are going to do the work and compress the spring. So you could do this a couple of different ways, but the crux of this is that the kinetic energy of the boxes is going to become the spring potential energy of the block and spring system. And so since this is equal to 1/2 kx squared, a larger spring constant for the same amount of energy is going to result in a lesser springs being compressed. So 2 points for part F, 1 point for saying that the boxes have the same amount of kinetic energy, and then 1 point for relating spring potential energy to the amount the spring is compressed. Okay, the formula, you knew it was coming, and they're coming up with 2. So I'll just write them out. So the first one says, well, D is equal to a constant times the mass of block A times the initial velocity of that block over this denominator. All right. And the second formula says, no, it's equal to this. Nope, I did that wrong. C2 times now inside K, and now MA plus MB. And then V here. So the question is for G, without manipulating anything or driving the correct equation, explain which equation better supports your explanation. Sorry about that. That helicopter went right over my house. Okay, so what did I say in parts E and F? I said large K, small d. So I need to look for a functional dependence that's going to be okay with that. So what happens if my K is large here? Since K is in the denominator, making that large is going to make my displacement smaller. So that is the one that we want to use. Just to double check, okay? Oh, and I should have made this a K, not a K for kinetic energy. Just to double check, what happens if I increase the spring constant here? Well, now I'm in the numerator, so that's going to increase the displacement. So that's no good. 2 points for part G. 1 point for saying equation 1, and again, addressing a functional dependence. 1 point for addressing the relationship between the distance and the K, which is what we said. Sorry, a lot of background noise today. All right, finally, part H. Now we have a graph of the displacement of the blocks versus time while block B is still in contact with the spring, okay? The solid line corresponds to either case 1 or case 2, while the dashed line corresponds to the other case. So we need to identify what the solid line curve corresponds to. So what you can see, since this is a displacement versus time, the solid line curve is displaced a smaller amount. So that corresponds to case 2, right? Because compression is less, right? And that goes with case 2, which is the stiffer spring. So 1 point for saying case 2 with an explanation, and then 1 point for addressing either the amplitude of the oscillation, which was the way I explained it. It compresses less. Or you could also deal with the period. You could argue that the period for case 2 would be less than for case 1. But I used the amount of compression. So that's it for the first one from assignment 14.